So today we're going to continue our discussion of cyclohexanes. This is our next part of conformations. Specifically, these are special because this is a conformational geometry, conformational biases that deal with six-membered rings. If you remember last time, we discussed what happens in acyclic, so butane, ethane structures. Around a single bond, we have different geometries that are possible. These are not really called isomers. Remember, isomers are completely different connectivities, but same molecular formula. Conformers come about when we get different geometries around a single bond. So if we have a sigma bond, and we undergo rotation about that sigma bond, we have a different presentation. It's not a different molecule, it's just barrier rotation because it has to move through a staggered or an eclipsed structure. This is where we get bonds bumping into bonds, groups bumping into groups. We also introduced one last kind. So up until now, you guys should know 3 different kinds of what we call strain energy. So the first one, when we talk about, let's say, a simple molecule like ethane, oops. If we have bonds that bump into bonds, as we go through what would look like a staggered one, this is a minimum in this energy. If we rotate it 60 degrees and we line everything up, Newman projection shows everything's overlapping. This is eclipsing. When bonds are bumping into bonds, we call this one kind of strain, right? It's known as Pitzer strain, or again, eclipsing strains. If we had large groups at these positions, so now if we were to add other functional groups, like a methane or a methyl group, what this starts to do is increase steric strain. This was the analogy we used was, imagine if you were on, getting on or off the bus, and you are walking around with an umbrella. So if we took a butane molecule like this, once again, in this conformation, everything is eclipsing. So that's where we're going to have bonds bumping into bonds. We also now have steric strain, groups bumping into groups. If they get close enough to each other, we're seeing a local repulsion of these groups with each other. The last one we introduced with regard to rings was ring strain. This is where you, because of how a ring is set up, we compress the bond angle. We make it smaller than it would normally have to be, the 109-degree bond angle you'd see in an sp3 center. And what this does is it sort of adds spring tension. It adds extra energy to the ring because if you built your molecular model kit, what you'd see is that we actually have to compress these bonds in such a way that something's going to have to snap, right? We're not allowing that sort of perfect bond degree overlap. As a result, the molecule picks up some degree of instability. Now, cyclohexanes are special because they minimize the instability due to the ring strain. Every bond is a normal 109 degree. So in this conformation, where we have from the side, we see this sort of up-down sort of structure. This is when we draw it on this angle. We call this the chair structure. We have this sort of seat part right here, then the flat part in the back. What we're doing is we're showing in chair structure from the top. We'd normally look at it in this geometry. This would be our sort of line bond type notation. In chair structure, we're sort of trying to highlight this end-on angle. The reason why is because there are actually 2 stable chairs. So we've now denoted these green bonds and these red bonds to differentiate between the 2. And you see in the way I've built this model, all the green bonds here are pointing away from the bonding axis. The bonding axis is this plane along here. The red ones kind of spread out around the outside. So we call these red ones positions, bonds which are sticking away from the plane of the ring. These are known as equatorial positions. Up and down, these are axial positions. So winds that are 90 degrees pointing away from the ring is called axial. Away or further away, sort of spreading out from the ring, we call equatorial. The reason why this matters is right now, in this particular chair structure, even if I rotate it in my hands, all the green axials will point up and down, all the red equatorial points away from the ring. But there's still flexibility. I can still sort of move parts of this ring. I can bend it back and forth. And it's possible to actually do what's called a chair flip. If I were to grab the apex piece of one of them, piece of the other, this was the magic trick we did last time. If I pull one side down and I push one side up, the result is everything that used to be axial will turn into an equatorial position. Everything that was equatorial turns axial. So all the green positions, I can make them equatorial by pull one down, push one up. This one just popped out. But as a result, I've inverted which groups are occupying axial and equatorial. They are still chair structures. Yes?
Is it possible to just have like both up or both down?
So, like you mean like this?
Yeah.
Yeah, so that's a good choice. If we did this, imagine both the tips are up. In this position, from here, this is what we call a boat structure. If you look at it, it kind of looks like a canoe. The reason why this is unstable is you can see it by turning here. Look down these bonds. What do you see? If I do a Newman projection down this bond, is this staggered or eclipsing? Yeah, and in fact, over here too. The entire front and back part of this molecule, when both are up or both are down, this is an eclipsing structure, which is very high in energy. It has bonds bumping into bonds. In the same way, eclipsing structures can be made stable by making them staggered. So in this position, in our chair structure, sighting down any of these bonds, what you'll notice is we have a staggered orientation around every one of these ones. Over here, staggered orientation. Any bond we look at will have that same staggered orientation around it. So that's why the chairs are low energy conformations. The thing is, there are two possible ones. If these are all hydrogens, there's no way to distinguish between one chair or the other. But if they're not, that's what we've designated with these axial equatorial. If these were different groups, there's a consequence of having either red axial or green axial. And the reason really this comes down to is look at how close the green ones are, the axial positions relative to each other. If I were to have something really big in one of these positions, it's going to start to bump into something else in one of these other axial positions. Versus, if I do this, I can take what was in that axial position, throw it out away from the ring. This gives me an opportunity, if there's a substitution on the ring, to change the relative energy of these two chair structures. So that's what we're going to discuss through today. So again, cyclohexane's planar, top down. This is looking at our normal line structure. It does not tell you anything about which conformation you have, just where substitutions are. The chair conformations, there are two of them, always, and if there is a substitution on the chair ring, one of those two chairs, representing a group axial or equatorial, will be lower in energy. Yes?
What was the name of the second type of string with like the groups clashing?
Groups with groups, steric. S-T-E-R-I-C, steric strain. And then ring strain is our third. So, this is our structure. And going from our line bond structure into what we draw, this is how we're trying to present it. This little center piece, the thing that looks kind of like a Budweiser logo, it's done by very carefully drawing these structures. Now we're going to take a little bit of time and practice this drawing. The reason why is penmanship matters. We have to be able to show where that core structure is. So we're showing here in green, red, and blue. And then the axial equatorial groups are presenting away from it. Now this looks like a lot of actual hair. In other words, we can actually use the implicit hydrogen rule and not draw every single hydrogen. It simplifies the structure. But most importantly is, you can see in this one here, axial groups are clearly shown as presenting away from the ring, right? They have this lateral presentation in this direct perpendicular up and down if the ring plane is sort of across here. The equatorial spreads out over this. And to draw this ring structure correctly, look at the bonding angles. What you want to try and do is notice the cyclohexane chair is made up of a series of parallel lines. And that's why this structure matters, because what we're trying to do is when we build it up, the two yellow lines are parallel to each other. Two green planes, also parallel. The two black ones, also parallel. And those parallel sort of angles will also extend out into the equatorial ones. So drawing your structure correctly requires you to sort of practice this draw point by point. We have a couple different sort of videos of this on the eChirp. If it's difficult to practice through, please go take a look at that. But this is what I mean. If you have, let's say, one of these groups at this position over here, showing the equatorial position extending away from the ring, it is a parallel to the two bonds here and here, which make up the ring itself, as is this one here. So the overall sort of zigzag type pattern that you see is replicated throughout the entire ring. And practicing this thing of drawing each piece as a parallel object allows you to correctly build up and have the correct bonding angles. The reason why this matters is if we're not very clear of our penmanship at something like this, if I was to draw something, so when I draw my cyclohexane, usually I'll do a consummate V, another one, consummate V. There is my sort of cyclohexane. You can expand this structure a little bit. You can practice this through, or again, we try to do this. What if you do 2 lines, 2 parallel lines, and then 2 parallel lines? That gets you your cyclohexane. The reason this matters is, remember, what we've said is the axial groups will be 180 degrees. There'll be 3 pointing up, and then 3 pointing down. When we're in this presentation, the other thing we're implicitly saying, when I draw something like this, what I'm saying is that bond is to the back. If I were to draw this, these points here are in behind the ones up front. So we're looking at this ring from a canted angle where those 3 I've tried to highlight darker, these points here, these are closer to your perspective than the 3 carbons in back. When you're actually drawing your equatorial presentation, you're going to start off with these 2 positions, and notice this position here is parallel to that line, and that line. As a result, this angle and this angle will be repeated again here and here. And finally, this angle, this angle, here, and here are also repeated again. So there's a total of 2 parallel lines. There's 3 pairs of 2 parallel lines that make up the core ring itself, and the equatorial presentations repeat those particular parallels. Yes?
Is it okay to use wedges and dashes? Or
no, that's the thing. When you're in this one, just like in Newman projection, you drop wedge and dash because we're using presentation or geometry around here to imply that. If you start mixing the 2, it gets really wacky. But yes, I think that you keep to this point. Why this sort of structure matters, if I were to draw something that looked like this, for example, it starts looking really difficult to say, well, what am I trying to show here? I've got this straight up and down line on this point. Okay, I'm going to draw the axial and equatorial group, maybe. And then over here, axial and equatorial. If you're not clear about your lines, I don't know what you mean here. This is like really, really, really bad penmanship, and I'm unsure. What do you mean here? Is this the axial? Is this axial? It gets harder to sort of pick if you don't follow this sort of template. So that's why penmanship matters, because it's clarity of presentation. It's being unambiguous about what groups you're placing in what position. Okay? So once again, just for our colors, if we look at the core template, you've built that up. Axials will be up and down away from the ring, and if you count around the ring, if you notice, if I started and actually added this as this is carbon 1 right here, here's carbon 2, 3, 4, 5, and then back here 6, that's like counting around this ring 1, 2, 3, 4, 5, and 6. What we're showing is, as you count from carbon 1 to carbon 2, notice what happens with the axial group. One axial group points down on carbon 1. As you come up to carbon number 2, axial is pointing 180 degrees to it. They are anti to each other. Then over number 3, down again, up. So the axial groups will actually occupy opposite sides of the ring as you walk from carbon 1, 2, 3, 4. So 1 and 3, carbon 1 and carbon 3, their 2 axial groups are both on the same side of the ring, and they're nearest to each other. Even though from a carbon-to-carbon basis, 1 to 2, those axial groups are anti, when you get around to carbon 3, those 2 axial groups are now close. Yes?
So long as we're like internally consistent and like alternating, does it matter where we start, like up or down?
Not at all. That's a good point. And this is what makes sort of this kind of difficult. What I'm going to show you through is we walk through presentations going from line bond structure over to ring. There's a number of ways of doing this because this is a circle. Depending on which way you like to go, I like to count around clockwise or counterclockwise. I like to look at the ring from the top or from the bottom. There are a number of different perspectives that are all correct. Because we have a ring structure, it's about sequential orientation and relative position that really matters, right? What I'm saying is, if you put one axial group down, the next axial group must be up, or vice versa, but it's completely up to you. The thing that matters, though, is when we move through these 2 points and we go through this chair flip, the chair flip matters in keeping track of where those groups are, because this inverts what used to be axial and equatorial. This is how we move between the 2 different stable geometries, the 2 different sort of staggered geometries. Now again, for our notation, usually what we're trying to emphasize here, this carbon that used to be the peak down to the left becomes up to the right here. That's usually how we do this flip. Now again, is this the only way you can see this? No. As long as you redraw it in such a way that a group that used to be axial becomes equatorial and the relative positions are all correct, that is fine. But for the convention we're going to be using, this bottom corner marked in red becomes that top peak in red. Orange is still orange, yellow is still yellow, green is still green. So the flip that we think about mentally is you grab those 2 peaks as drawn in your chair structure, one goes up, one goes down, that becomes your new structure, okay? So again, why do we call it a chair? Because it sort of looks like a weirdly drawn chair in sort of a loungy kind of way. Now you can think about that chair flip as proceeding through this very high energy, what we call the boat. As we discussed before, if I took one of those peaks, if I either pull one up or push one down, don't do both, you proceed through what we call this boat structure. This is your overall eclipsing structure, the high energy structure. So it is not stable. It will move beyond that back to one of your other chairs. But you fold one up, you fold the other one down. So stop here. We do not form these kinds of structures. They are very, very high energy transition states. So again, visually, this is what we do, and focusing only on one of those groups. If I had only 2 substituents, everything else was hydrogen, this is usually how we'd end up drawing it. I know down here in the bottom, we're showing everything with hydrogen. But again, these chair structures don't matter unless there's a group that differentiates one of the positions. If they're all hydrogen, the energy for both 2 chairs is identical. There's nothing that's higher or lower energy because they all have hydrogen in all the positions. As soon as we substitute one of these hydrogen groups, if I put a methyl group here, now we have 2 geometries, one where the methyl occupies equatorial and one where it occupies axial. And because of that consequence, how close that methyl is to other things will change the overall energy of those 2. One is better than the other. So that's what the animation looks like. Pop one up, push one down. And again, practice this as you go through your actual sort of model kit. This push-pull activity just involves bond rotation. It should be something you should be able to do and see with just your model kit. Again, visually, when you're drawing these things, the thing you keep track of it is, in a chair flip, if you've drawn something where a group occupies the equatorial position, a chair flip will allow you to occupy an axial position. Both are possible. So that's all I'm mentioning again here. Once again, everything that was red is now axial. Everything that was blue is now equatorial as we move through these 2 positions. So this is where it matters. If we execute a chair flip where there's now groups that are not all hydrogen, there's different energies associated with this. So let's start with the top one. If I was going to draw this, where I'm just going to mark, this side is red, this one is green, and I'm going to redraw it where I'm going to push this one up, pull this one down. So if I started with the sort of Budweiser leaning down to the left, I'm going to now draw it the way I don't draw very well, like this. So I'm now leaning it to the other side, where this point here used to be my green, red point up here. Now again, as you're working through this, using colors, using numbering to kind of to register your position, it's very helpful. Just like we talked about going from line bond to Newman or Newman to line bond, it helps by drawing out a general template. So as we do this, now that I've kind of picked those 2 reference points, I've pulled one down, pushed one up, what else do I have to add to my general template that I'm drawing here to make it accurate? I need a methyl group. Where does that methyl group have to attach? Yeah, on the green one, wherever it was before. So that's where putting some point of reference in there is good. Is that correct?
No.
Why not?
Yeah.
It used to be the methyl in my first structure was equatorial. If I'm pulling it down, I'm changing the geometry. Anything that used to be equatorial must now be axial. So you don't just, oh yeah, it needs to be there, I'm filling it and I'm done. No. If this is a new conformation, a new geometry, the methyl group now must be down here. What is in this position here? What was in the equatorial position when I started? Sorry, axial over here, yep, was hydrogen. Equatorial is now hydrogen. Every center has two groups, even if they're not shown. And by, again, implicit hydrogen rule says there's a lot of hydrogens around here. Every other group or position has a hydrogen on it. Again, for simplicity, for clarity, you do not need to draw them all. But mentally filling it out, there are still two. There's always axial and equatorial groups, and they're just being filled in. Okay, so let's do this next one. Once again, I'm going to put in here, there's a hydrogen in the equatorial plane and a hydrogen here that's axial. I'm going to color code the two atoms I'm using again. So there's my green and there's my red. But those two positions are the ones I'm manipulating. That's the ones I'm going to use for my sort of my ring change. I want to color code the other two where I've got my chlorine and where I've got my bromine. Just because, again, I need to make sure that those positions are the ones I'm substituting. I don't need to pay attention to the other two in that case. All right, once again, I'm going to start by pulling this one down, push that one up. I'm going to redraw my other geometry. Again, if I started out with a ring geometry where it was sort of chair facing down to the left, it's going to be one chair facing down to the right. This point is still my green. This point is still my red. They were unsubstituted as I've drawn them. They remain unsubstituted. I don't have to change any part of it. Next thing. Where is my blue center? From the red, which one is blue? If I number this out, 1, 2, 3, 4, 5, 6. Which one is blue? There's either 2 or 6. Remember, when I take this one, red pops up, green pops down. From this perspective, this is the blue one right here. Remember, when you're looking at this, these bonds here, red up front here, by the numbers, carbons 1, 6, 5, and 4 are towards you. Just like over here, let me number those. This would be carbon 1, 2, 3, 4, 5, and 6. Again, that numbering is relative to just how I'm moving around this ring, but carbons 1, 6, 5, and 4 are closer towards you. 2 and 3 are in the back. That's the presentation position we're at now. Yes?
Would it still be correct if you drew them on like 6 and 3 instead of 5 and 2?
So let me draw a different perspective. Yes, that is still correct. Again, you can, as long as the relative position between the two is accurate, and I'll show you what that means just when we go to that point. But yes, it's possible, right? Again, what I'm showing you here is this is how I view through and put down sort of this is my line, just to kind of present the two. So the tip comes up, red goes up, green comes down. By our numbering, the blue one is in that carbon 2 position, around the back of how we've drawn it. That makes carbon 5 this position right here. So once we've picked those relative positions, the next thing we have to do is fill in the two geometries. Just for clarity, I'm going to get rid of my numbers for a second at these two. And now I'm going to add in my axial and equatorial groups. I'm going to put them in position so I could fill them out. From this one, this position here in blue, remember, we have parallel line, sort of parallel line, then we're going to have a parallel line here. The axial position will be in the back, sticking down at that point. Here at this one, what we have to do is extend this out. The axial position is easy. It's up this way. The equatorial position is going to be down this direction. These are the hardest two to draw in this structure. It's something you practice through. But the 4 parallel lines from these two positions, this angle here is this one and this one. Those are the two other equatorial positions associated. Axial, straight down, and straight up. Those just fill in the sort of sticks. Those are the positions we have to add. Now all we have to do is add the right group in the right position. I had a chlorine that was axial on carbon 2. It's going to now be equatorial. Hydrogen is over here at that last position. The bromine used to be equatorial. It is now axial. So 3 steps. Redraw the new geometry. We're pushing and pulling in 2 positions. Identify the centers that have to be substituted. Draw in the correct axial equatorial pieces. If it was axial, it becomes equatorial. If it was equatorial, it becomes axial. Yeah, questions? Bring them, bring them. What looks wrong? What is bugging you about this drawing? Nothing. Awesome. So here's what I mean. What I said about there's more than one right answer. Let's go to the actual sort of molecule kit here. All I mean by that, so let's use same kind of colors. I'm going to use my blue for my chlorine, and I'm going to use red. So I'm going to make the first molecule. Back over here, in this molecule, I want to build a model kit where 1 is down to the left, on carbon 2 to the back has a chlorine. I'm going to say chlorine is my blue atom, and it's axial. And then counting around to number 5 as my bromine. Bromine is going to be red. It's going to be equatorial. So this is what I mean. From this perspective, here's carbon 1. Counting back, carbon 2 has chlorine in an axial position. Then around back here, carbon 3, I'm holding carbon 4. Up front to carbon 5, bromine is equatorial, and then carbon 6 here. This represents our starting geometry we showed. Tip down over here, tip up over here. If I do my ring flip, I'm going to start with my left hand and bend that up. Take my right hand, bend it down. Whoop. Once again, axial has become equatorial. Equatorial has become axial. This represents the geometry we stop at. This tip is now up. This tip is now down. And you notice that we have what used to be our bromine group is now up axial. What used to be my chlorine is now back equatorial. The parallel lines I was pointing to, parallel line here, here, and back there. So it's a perspective view of this one. Now again, this is if I were to not move my hand. So I'm holding on to carbon 1 in my left, carbon 4 in my right, and I'm just going up, down. That's my new geometry. Okay? But because this is a ring, if I were to just index it over, I'm going to hold it now by the carbon with my chlorine and the carbon with my bromine. In this perspective, take a look. I can draw this. Tip down here has the chlorine in the equatorial plane. Tip over here has the bromine, and the bromine is axial. This is a correct way to draw it. And all I had to do to draw from here to here is just rotate my perspective. Because it's a circle, it is up to you to define what position you're calling carbon 1, and relative to that one, carbon 2, 3, 4, 5. What I mean is, the most important thing about this, in one chair structure, chlorine must be equatorial. 4 carbons away, 1, 2, 3, 4, around the ring, must be my bromine. And if chlorine is equatorial, bromine must be axial. If I undergo a ring flip, the relative position doesn't change. Chlorine is still 4 carbons away from bromine. If now bromine is equatorial, chlorine becomes axial. This is a flip-flop gate between these two. If one is up, the other one has to be down for this geometry. And more importantly, I can define it anywhere around this ring. Holding any 2 positions in opposite cases gives me a correct chair structure. So sometimes, if you're better at doing this in terms of rotating it, in the particular example here, some people start off, if they see that chlorine and bromine are 4 atoms away, it's easier sometimes to just rotate that one such that they occupy the 2 tips, because it's easier to draw when they're at those sort of 2 apical positions. Then you do your rotation, then you're correct. The most important thing is the relative position of those groups must remain the same. They are 4 atoms away. And we start, chlorine is axial, bromine is equatorial. Its ring flip must have those in opposite positions. So there isn't sort of a one and done. This isn't something that always has to have a singular perspective because we're looking at this cyclic ring, and your perspective can define how you choose to draw it. So this makes it something that we have to look carefully at. And again, having your ring, your model kit with you is very, very helpful because it allows you to easily manipulate and rotate, change your perspective, and draw accordingly. Okay? So if you look at this one, we start off with two chair structures. And again, using the nomenclature, the perspective we've done now, I would start by grabbing the carbon with the red and blue substituents on it. I'm going to hold on to this position here. And I would hold on to the other one. As I go through the ring flip, I'm pushing this one down. I'm going to pull this one up. That remains where you have those two. Relatively speaking, that is how I'm drawing these 2 points of perspective. Again, counting around this ring, if I were to start at that orange center and count around the back, I would call orange number 1. In the back is 2 and 3, over to carbon 4 and blue, and then around the front again, continuing along my line, 5 and 6. So by my numbering, carbon 1 has my red and blue, and carbon 5 has the green. If you choose to number the other way, totally cool. Just be consistent in about the direction you're moving around the ring and how you're labeling these ones. That's why numbering, colors, different ways to sort of have your point of reference. So the most important is, in your chair structure, we can define two conformations. We can talk about these conformations about relative energy and stability. One will be higher in energy than the other, provided there are different groups here. Those two chair structures correspond to one and only one line bond structure. When you look at the line bond structure here, we provide no information about chair or eclipsed. We don't know if it's axial or equatorial when we're looking at it from this sort of top-down view. What do I mean by that? So let me actually build this same molecule, same colors. So we're going to do blue, red, and I need a green. Okay. All right. So as we started out, here is the chair structure. Whoops. Yep. Hold on. That has to go over here. All right. On the slide we started out with chair structure. This carbon here, what I'm holding with my fingers, has a red and a blue. Red is equatorial, blue is axial. Counting around the back of the ring, carbon 2, 3, 4, up here to number 5. We have our green. Green is in an equatorial position. So this is how we started our first chair structure. If we do a ring flip, this goes up, this comes down. Now as we draw this, axials are now my red and green. Blue has now become my equatorial. So those represent the two ones here. And again, from chair structure, I can tell the difference between this and this. And then we can talk about different energies. When we talk about line bond, what we're saying is the perspective changes. Instead of looking at this side on, instead of defining which of these positions is axial or equatorial. When we're talking line bond, it's like taking this molecule and physically squishing it so that it is flat. Remember, when we draw a line bond structure, what we're saying is all 6 carbons have a straight line, which means they're all in the same plane. They're in the plane of the page. When we draw it like this, down here in line bond, every atom that we've defined for our 6-membered ring is none are in front, none are in behind. They are all in the same plane. So by doing that, the reason we do this is it allows us to quickly show atoms like this. We're literally taking the entire ring and smushing it flat. This does not represent a conformation. This is a convenient way to say which ones are on which side of the ring. So when I do this and I squish it flat, this represents what I'm actually showing in my line bond structure. Now, notice this. Red is what? Wedge or dash? Is it coming up towards you or back? This is a wedge. Blue is a? Green is a? So wedge and dash is from the perspective of taking your normal happy chair, one of these guys, right? This is saying one of my conformations. In chair structure, I can show 2 geometries. One is equatorial, one is axial. When we're talking line bond, You do not care, and you do not talk about which is axial or equatorial. Instead, we get it so that it's effectively a plane. All the carbons are on the same plane. And what we're trying to define is, if all 6 carbons are on one plane, which of these groups are above the plane of my carbon ring, and which are below the plane of that carbon ring? The reason why is, if I looked at it from this perspective, this would be, we said wedge or dash. This is wedge. This is, and if I do this, did I change the molecule?
No.
All I ended up doing is now this is expressed as a wedge, dash, dash. It's a pancake flip on the molecule. I haven't changed any bonding. All I've done is said that this is still one molecule, this is one geometry, this is one isomer. But line bond structure is not meant to talk about different conformations. So we use them differently for different purposes, okay? Line bond is meant to express only the relative perspective. Chairs are meant to respect which geometry may or be more or less stable relative to something else. So what this means, most importantly, sorry, let me go back to that just for a second. In this geometry, red is what? Axial or equatorial?
Axial.
Green is?
Axial.
Blue is?
Equatorial.
If I do this, squish it flat, this is a wedge, right?
Yeah.
This is also a wedge. What would this be?
Wedge.
Wedge and dash does not mean axial or equatorial. Remember, based on our color code, greens are all axial, yes?
Yeah.
That's definitely equatorial. If I squish this flat, look at which bonds. If I count around by color, when it's flat, wedge, 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 wedge. The crown around the top, every position that used to be axial or equatorial is now just a wedge, because when we squish this molecule flat, anything that's above that plane of the ring, when we've removed all that sort of zigzag pattern, will now be the same geometry. They're all on the same side of the ring. Wedge and dash does not implicitly say, oh, I've got a wedge, that's definitely axial. No, it depends which carbon you're on and which chair structure you have to be. Do not confuse the two sort of notations. Wedge and dash is meant to show relative geometry around the ring. Axial equatorial says, once you're in a chair structure, who's close to who's further away. So that's what brings up this kind of isomerism. We have special names for relative positions. This is a way for us to talk around the ring and say, where are they relative to each other as defined in line bond? When we squish the ring flat, we can now say, look, these guys here, the methyls on this first one here in red, they are both dashed, which means if the plane of the ring is flat, if we think of that as a flat ring, both methyls are on the same side of that ring plane. Just like over here, this oxygen and this CH3, both in red, are on the same side of the ring. The two blue groups, chlorine and oxygen, these two oxygens, same side of the ring. We're not saying top or bottom, they're just saying relative to each other, they have the same relative presentation. We call this cis, C-I-S, which means on the same side of some linear presentation. This works for rings, it also works for double bonds. We're saying if we have some plane that we can define the relative position of two things that are cis, just means those two things are on the same plane of what we're ever describing. We also have opposite side. We call this trans. So if we have a methyl that is down and an oxygen that is up, or oxygen methyl, or chlorine oxygen, if one is wedge and one is dash in this 2D ring bond plane, we're saying that one is above and one is below. Meaning these two groups are trans to each other. You can use this notation for any degree of substitution. It's a way of saying, for example, if I'm the methyl and I'm standing here, relative to me, the OH is on the opposite side of the rings. We are trans. It is a way of defining and talking about relative position of any two groups in any structure, no matter how complicated it could get. So what I mean is, again, if I were to draw line bond, and I'm going to put in a chlorine, an alcohol, and a methyl. This is a specific molecule. Methyl to chlorine, what is their relative relationship? Cis or trans? They are what?
Trans.
They're trans. Oxygen to chlorine are?
Cis.
Oxygen to methyl are?
Trans.
That's it. You can pick any two positions and say relative to these two, based on how the ring is presented, they are on the same or opposite sides. This allows us to say, okay, well, an isomer of this would look like chlorine, OH, methyl. In this change, going between these two, methyl and chlorine are still what for both of these two? Methyl and chlorine are, but the methyl to the OH are, and the other one trans. These are different at that one junction. So you could refer to these two as, oh, I need the alcohol, which is trans to the methyl. That is the chemical that I need. As soon as I do that, you guys will focus in on this one on the right. It's a relative positioning argument that allows us to sort of talk through geometries, okay? So once again, wedge and dash do not mean axial or equatorial. You must convert between these ones in order to see it clearly. So let's start with the two fluorines. When we're in this geometry, in line bond structure, we're not in line bond structure yet. Designating if they are trans or cis is difficult. If we're in chair structure like this, we must convert over to line bond, then and say, is this cis or trans? So I'm going to take this one here as our example. All right, how we do this. Again, this is how I do it. This is my method. I start off by identifying some common reference points. And again, I like taking those 2 points, those 2 pieces. From my perspective, what I usually do is I'm going to something that looks like this, right? And in my head, the way I like to do this is imagine that you are looking down at this ring. I'm imagining I'm going to be, like, this is a side-on perspective, but I'm going to put myself in the perspective where I'm looking down on that ring, which means I'm in the plane of the page, I'm staring down at this point. If I was to do that, there's also going to be a rotation. I'm going to choose to rotate this such that my blue one is in this position, and the green one is down here. Again, you can choose any point, a point of reference. I usually go through this as a standard of saying, look, whatever used to be drawn on the right-hand side is going to become my point at the top of my line bond structure. Whatever's down on the left becomes my bottom. That's my 1 and 4 positions. As soon as I've done that, the rest of the molecules should start to come together. If I was counting around this one, and I'm going to put color codes on them, here is orange. I'm going to run out of other colors. Here's red. So if I go around this point from the top, my red one should be here. My orange one should be there. If I go to, since I'm out of other fun colors, I'm going to put an X right there and a red X right there, which would correspond to X and X. That completes all of them. Again, you do this by numbers, you do it by coloring, whatever gives you a common frame of reference. So now that I've transposed the two and I've got a basic template, now I can start to fill in pieces. Where do I need functionality? Which colors or circles or whatever do I need a fluorine attached to? There's 2, right? So I need which ones? Red and blue. Red circle, blue circle, right? Okay, so I know I need to put something on this red circle right here, and I have 2 choices. In this perspective, I'm going to have what should be a wedge position, and I'm going to have a dash. Just like on my blue one, I'm going to have a wedge and a dash. I may not know what goes on those positions, but I know there has to at least be one of each. It's an sp3 center, it's tetrahedral. So now that I've got those ones in, start on the red. If I'm looking down on that center, fluorine is coming straight up towards me. Should that be a wedge or dash from that perspective? Yeah, if I'm looking down, this is my creepy eye right here, and I'm looking down at this point here, I'm staring right at the fluorine. So from that perspective, fluorine should be wedge. Hydrogen away from me is in this position here. It is to the back of that fluorine. If I was looking right at that position, the fluorine would be in behind. The fluorine was up towards me, excuse me. The hydrogen's in behind. Likewise, let's go over to this position here. Creepy eye. If I'm looking only at that blue one, what is staring me in the face? What should be a wedge position? Yeah, there's a hydrogen here fluorine is away. So in that blue position, this should be my hydrogen. Fluorine is to the back. Now, cis or trans? The two fluorines are your trans. The way that you transpose, going from any of these structures to their line bond, remember that on each center that we're looking at, there must be axial positions. Those axial positions are your hydrogens, if you're only given one. And depending on your perspective, if you were to look at it from the top or from the bottom, you'll see a wedge or a dash depending on this. If you are looking down from the top, anything that's axial coming straight towards you will be up. Now again, that doesn't mean axial is always a wedge. Let's take this one right here. If I were to put a methyl group right there, and I were to look down on this position here, this is axial, but from the perspective of what I just drew, looking down on that one, what is the thing that's closest to me? If I was looking only down this bond here, where I've added this methyl, closest to me is hydrogen. Methyl is away from you at that perspective. And really what you're saying is, any carbon that is peaked up towards you, if you're looking from the top, the axial will remain in this sort of wedge position. If the carbon is bowed away from you, down, the equatorial will look like its wedge position. So that's where back to where we said, the axial positions will flip-flop on either side of your ring plane. One is up, carbon 2 is down, one is up, one is down, and that's why you get this inversion where axials will show as wedge or dash depending on the perspective of the ring. Same thing too about what we just finished. We said this is trans. If I were to look at it from the bottom, would this suddenly become a cis molecule? If I were to pick up the whole thing and flip it over, still trans. So this is all about relative perspective, right? Just by choosing where you look at it from and what you call carbon 1, carbon 2, that will not affect the outcome, just the relative presentation. The analogy I always use, this is my left hand, still my left hand. It's just about the direction that you're sort of focusing and looking at, okay? So the last thing we have to talk about, and this is where we're going to end off. Yeah, double Newman projections. Like we just talked about before, the reason that chair structures are stable is because they adopt a staggered geometry. So we have three different ways to show this. One is, the line bond structure gives us the ability to say very quickly, is the molecule cis or trans? Are they on the same or opposite sides of the ring? Second one, chair structure, we can now see the difference between our two geometries. What happens though is we need to be able to say, okay, if I have one chair structure or flip opposite, that's one way to talk about it. But to be more specific, what I can do is cite down two parallel bonds across the actual ring. What that does is you can clearly see this is now staggered, as is this one here. And what you notice is the axial groups will present away from our double Newman, the equatorial along the ring plane. A double Newman perspective is drawn by building up, taking this and picking any two parallel rings. So the two green bonds, or the two yellow bonds, or the two red bonds. If I position my point of view such that I'm looking down those two, it's just two different Newman projections at the same time. All right, we will kick off on this one and start building up how we build these projections. I will see you guys later.
Thank you.